All right, for this problem, it says here that we have an inclined plane, which is inclined at a certain angle represented by theta. We have a hoop of mass m with a radius r, and its moment of inertia is mr squared. Now, the first question is you have to draw and label the forces acting on the hoop. Well, going back from our previous discussions before about linear motion, linear mechanics, this is actually very easy. We already know that the forces acting on this sphere is actually we have a normal force which is perpendicular to the surface area. So this normal force is perpendicular to the inclined plane. We also have weight, and since there is an angle, therefore your weight should have an x component and a y component. We also have frictional force. So in other words, this is the schematic diagram or the free body diagram of the forces that exist in this particular system. So as you can see, we have normal frictional weight. Our weight on x is denoted by mg sine theta, and our y is denoted by mg cosine theta. Now, the second problem is asking you to show the linear acceleration of the hoop as given by the equation A is equal to g times sine theta over 2. So we have to prove that we will be able to obtain this from the system. Well, to approach this problem, you have to start first with equilibrium of forces, which states that the summation of the forces is equal to ma. Now, we start with your forces along y-axis. We actually know that we only have two forces in the y-axis, which is the normal force and the y component of your weight, which actually cancels each other out, thus equating it to 0. So if that's the case, if your forces along y is equal to 0, that only implies that your normal force must be equal with your weight along the y-axis. Now, we set this aside and we move on to the forces along x-axis, which is obvious. We know that along the x-axis, we have your weight on the x component, and we also have our frictional force. We know that frictional force actually refrains or resistance to motion. Therefore, we denote it with the negative sign, implying that this resists the motion of the object to roll down. So after that, after we are able to equate the equilibrium of forces, we now move on to rotational motion. We know that the body here is actually rolling down, therefore it has to have a torque. And we know that torque is actually equal to I times alpha, which is denoted by these quantities. We also know that torque also has another formula, which is the product between your force and your lever arm. In other words, since both of them are equal, we can actually equate them together. So we can say that Fr is equal to I alpha, dividing both sides with R. We can now have a formula for our force because we want to know, as we can see from our equilibrium of forces, we have here a frictional force. Thus, we can conclude rather that the force that exists in this system is accounted to the frictional force. Since we already have F is equal to I alpha over R, we can now substitute this formula, this equation number 3 to equation number 1. Therefore, this gives us MA, X is equal to weight on the X component minus I alpha R. Now, substituting your X component, we know that your weight is equal to mg sine theta minus I alpha R. Simplifying further, we can say that we can divide both sides with m in order for us to isolate a. It gives us ax. Finally, after simplifying everything, this will give us a is equal to g sine theta minus r squared alpha over r. Now, you might be asking, where did this r squared come out? Like, where does m come out? We know that I, from the given problem, it says here that the moment of the inertia of the hoop is equal to mr squared. Therefore, we replace I with mr squared here. Dividing like terms, this leaves us a x is equal to g sine theta minus r squared alpha over r. Simplifying further, this gives us ax is equal to g sine theta minus r alpha. Now, how do we move on? Well, we know that your ax here is actually the linear acceleration. And we know before that the relationship between linear acceleration and angular acceleration is actually denoted by r alpha. Thus, your r alpha here, we can just simply say that that's the linear acceleration. We just replace r alpha with a. Simplifying further, we have ax is equal to g sine theta minus a. Um, Combining like terms, we transpose your a to the left side. That becomes a plus. So ax plus another linear acceleration plus a gives you 2a is equal to g sine theta. Dividing both sides by 2, this finally gives us a is equal to g sine theta over 2. Therefore, we are able to justify that the linear acceleration of the hoop is equal to g times sine theta over 2. Now, moving on, we have to calculate the acceleration of the hoop when the theta is 20 degrees. Now, since we have already simplified, we have derived a formula for your linear acceleration. We can just use this and input the values. We know that g is 10 meter per second squared. Sine 20 degrees over 2. Finally, this gives us a is equal to 1.68 meter per second squared. Now, this is the acceleration when the theta is 20 degrees. Alright, from the problem, we also want to state the relationship between the force of friction and the angle of the incline. Previously, we have already derived and simplified that the only force that exists along the x-axis by now is the frictional force. So frictional force is equal to ma. Since ma is the second law of motion, we know that a from our previous derivation is equal to g sine theta. We can just simply substitute this value here, so it becomes frictional force is equal to mg sine theta over 2. Now this shows the relationship between your force of friction and the angle of the incline here, which is denoted by theta. Now moving on. Let's move on to the last problem. It says here that the angle of the incline is slowly increased from 0. So we have to determine the angle in terms of the coefficient of friction, wherein the hoop here will begin to slip or slide. So for us to do that, we have to first we have to go back to our derivation for the forces that exist along the y-axis. If you remember, we know that n minus weight is equal to 0. In other words, both your normal force and your weight along the y-axis are equal. Thus, n is equal to wy. We know that the y component is equal to cosine theta. Therefore, n is equal to weight times cosine theta. Now, in order for us to determine the angle, we have to use the formula before for coefficient of friction. If you remember, the coefficient of friction is obtained by the general formula. Frictional force is equal to the coefficient of friction times n. Simplifying further, frictional force is equal to coefficient of friction times your n here, which is now your w cosine theta. Finally, after that, alright, now that we have obtained the formula, the first formula for friction, which is mu w cosine theta, we cannot forget that previously we already have derived a formula for frictional force based on the angle of incline. Thus, we will be using this equation as well. So, uh, now that we have two equations, we now know that they are both referring to frictional force. We can just equate them together. Equating them together we will be able to finally have a relationship for us to determine the angle at which the hoop will begin to slide forward. So for us to do that, we have to isolate all the quantities with angles together. So therefore, we have to cross multiply. This gives us 2 mu w cosine theta is equal to mg sine theta. As I was saying, we have to join together all the quantities with angles. Therefore, we divide both sides with mg and both sides with cosine theta. Finally, this will leave us with 2 mu w over mg. is equal to sine theta cosine theta. And actually, sine theta cosine theta, if you're going to use trigonometry, that's actually equal to tangent theta. And simplifying further, this will leave us with tangent theta is equal to 2 times the coefficient of friction. Therefore, we will now be able to get the coefficient of friction just by using the relationship between tangent theta and the coefficient.